All right, I want to thank everyone for coming today for this special joint RAL M-Cubes seminar, and those online as well. We have a special guest today who many of you are familiar with. He has a long history with NCAR, Clark Evans, who is currently the new research physical scientist and model physics branch chief at Earth Prediction Advancement Division here at NOAA in Boulder. So he works in a lot of areas, chiefly tropical cyclones, synoptic meteorology, mesoscale, just convection, and NWP. Some of those things he'll be talking about today. His history goes back to Florida State University, where he finished his PhD in 2009, and also did his bachelor's through master's degrees there. Then many of you got to know him from his ASP postdoc here from 2009 to 2011. And after that, he went to my undergraduate alma mater, University of Wisconsin-Milwaukee, where he became a distinguished faculty member for 13 years and was chair of the atmospheric science program there, a really fine, small program. And is also commissioner for AMS's Scientific and Technological Activities Commission. And finally, another connection to Boulder here is he's a member of DTC's Science Advisory Board. So with that, I'll turn it over to Clark, and thank you very much.
All right, well, thank you, Chris, and thank you, everybody. It's great to see so many familiar faces, as well as a number of new faces here as well. I'm happy to present on some of our work at the Global Systems Lab across town, utilizing MPAS for real-time hurricane prediction at high resolutions. I know there's been a fair bit of hurricane-related research with MPAS here in Foothills Lab here at NCAR. We're trying to push it to see what we can actually get out of it real time, both for the modeling system as well as the physics that we've been developing at GSL for a number of years. And so I really get to come in as the figurehead of all of this. A lot of the hard work for implementing our real-time MPAS forecasts was done by others at GSL, and I'd be remiss if I didn't thank them specifically. Janet Derrico, our code manager, Christina Holt, who works a lot on our workflows, James Kenyon on post-processing, Molly Smith on verification, Sam Trahan on all things model system related. Kai-Yi Wong is our data manager, and then all of our physics developers who will have specific call outs a little bit later on. So this is truly a team effort across not just the Earth Prediction Advancement Division that I'm a part of at GSL, but extending to our Assimilation and Verification Innovation Division, or AVID, comprising a lot of the core of the science efforts at GSL. So a little bit about our legacy at GSL modeling-wise. We've largely been known as the regional or storm-scale modeling shop within NOAA. Our legacy dates back decades to the rapid update cycle, the RUC, more recently the rapid refresh, currently at 13-kilometer horizontal grid spacing, run hourly. Those provide initial and lateral boundary conditions where the RAP domain largely covers North America and adjacent waters. For our 3-kilometer rapidly updating high-resolution rapid refresh, or HRR model, that is sort of the gold standard for storm-scale operational numerical weather prediction here in the United States as well as across the globe. And we also use those data to provide initial and lateral boundary conditions for even higher resolution forecasts, most of which are not operational but help facilitate certain projects or certain activities, such as our participation in the Wind Forecast Improvement Program, the first through the current third iteration. And those, as you go to finer and finer scales, get smaller and smaller in their extent. Our HRR domains are the lighter green over Alaska and CONUS. Our 1-kilometer domains are even smaller, covering usually a couple of states in their horizontal extent. We've done our own model system development, our own data assimilation to provide initial conditions that are consistent with our physics. But we've primarily applied these over land, namely CONUS, with stakeholders that are CONUS focused. FAA was a big supporter of our HRR development for aviation needs. NWS, there's an extensive list of forecast discussions that reference the RAP and the HRR, updated to this date. Energy, all across the board. But our grand challenge within the lab, sort of our guiding principle, is to deliver actionable global storm scale prediction and environmental information through advanced technologies to serve society. So storm scale has been our wheelhouse, but global has not at all been our focus. So if we're going to get there, if we're going to meet that grand challenge, we need to better understand how our modeling system, our physics, the dynamics of the model, our workflows, which include verification and post-processing, and eventually data assimilation, perform across the globe in different regions with different meteorological conditions than what we see over the CONUS and North America more broadly, and for different phenomena than we typically see here over the CONUS and North America. Tropical cyclones being just one of many of those. NOAA, of course, has its own unified forecast system powered by the finite volume on the cubed sphere FE3 dynamical core. But NOAA research, in collaboration with others in the university, and I think some here at NCAR as well, has demonstrated that FE3, that dynamical core, is not well suited for predicting some of the more high-impact meteorological phenomena that we're interested in, namely thunderstorms. They're too coarse. They produce too much rain, too intensive updrafts, too much warming aloft. And those issues seem to be fundamental with how that model is set up. And so, looking for us here at GSL, as well as other NOAA labs, we've begun to adopt MPAS, the model for prediction across scales, for a lot of our storm-scale numerical modeling efforts. I'm not going to belabor this because I'm imagining a lot of you are pretty familiar with the rich history of MPAS here at NCAR. This exists as a standalone model, but also as a dynamical core that can be implemented, such as in CESM. We began real-time MPAS forecasts in spring 2024, shortly before I started at GSL in July of this year. We have 4 real-time systems that have run this year, 3 that are focused over CONUS plus, so adjacent waters, southern Canada, northern Mexico, testing different initializations and different physics configurations. But we also have one that we've run for NOAA's Hurricane Forecast Improvement Project, a long-running project to advance NOAA's hurricane modeling capabilities. And it's that run in real time for hurricane applications that I'll present on here today. So in terms of how we have MPAS set up for our hurricane applications, we're utilizing the regional MPAS configuration on the version 8.1 code base, so a little bit behind the current release, but not significantly so. 3-kilometer horizontal grid spacing with 80 vertical levels over this elliptical-like domain here, extending from the southeastern third to half of the United States toward the Cabo Verde Islands in the eastern North Pacific Ocean, or North Atlantic Ocean here. We've ran this primarily from early September through late October. We had a lot of development work that took place over the summer to get our real-time system running smoothly. So we weren't able to start earlier in the hurricane season, but this year's Atlantic hurricane season was really backloaded from the typical peak in mid-September through October. So we captured quite a large number of storms from Francine through Oscar primarily. We're utilizing the GSL physics suite that our developers internally have been working on for many years, and I'll go into a little bit more detail about that. This is the physics that has been ported over from the Rapid Refresh Forecast System version 1, which NOAA and National Weather Service just decided right before Thanksgiving that they will push to a formal science evaluation for a potential operational implementation later in 2025 or early 2026. We use no convection parameterization. There have been some RRFS applications, even at storm scales, to try to use convection parameterization to assess if it can help mitigate some of the issues and biases seen with precipitation. We don't see those with MPAS. We ran it in real time parallel with that for CONUS applications. We don't see a need to do that here. Importantly, we have no atmosphere-ocean coupling. This is just atmosphere only with static initial SSTs. Cold started from GFS, so we're not yet doing our own data assimilation. Our team internally at GSL is working with JEDI, another effort with which NCAR is heavily involved in, to be able to stand up real-time data assimilation. And it looks like that'll be Q1 of 2025 that we'll be able to implement that. We're doing this twice daily, 0 and 12 UTC, out to 5 days. We've developed this MPAS app, a workflow that helps to manage our real-time forecasts, which is based off of the Unified Workflow Tools, part of the larger Unified Forecast System that NOAA and EPIC, the Earth Prediction Innovation Center, help to support. It includes MPAS as a model, post-processing through MPAS-It, a tool developed initially at NSSL for regridding the data to a uniform lat-long grid, UPP, NOAA's Unified Post Processor, to do more derived variable computation. We use GFDL's Tropical Cyclone Tracker that Tim Marchuk has developed for several decades now, and then GSL's internal Python graphics suite, PyGraph, although we also have a number of other individual visualization packages that we can use as well. Our physics. So GSL has a rich history of developing physics for RUC, for RAP, and for HER, continuing to the Rufus era, and now as we look toward MPAS potentially serving as the basis for the second iteration of the rapid refresh forecast system. And for our hurricane-related applications, it includes these 6 classes of parameterizations listed here. The RUC land surface model that Tanya Smirnova has developed for multiple decades, MYNN surface layer, as well as the boundary layer and shallow cumulus parameterizations, for which Joe Olson is the lead developer. Our unified gravity wave drag package, for which Michael Toy, also a previous NCAR postdoc and employee, is the lead developer for. Radiation we don't specifically develop. That's the group at AER, Eli Mlauer and Mike Iacono. We have developed machine learning emulator for that, but we're not currently using that in our modeling systems. And then the current iteration of the Thomson-Eidhammer Microphysics for Operations, or TEMPO, for which Anders Jensen, who I think also has a history here at NCAR, is our lead developer. We also do have other parameterizations that are not used in this system. Our cumulus parameterization, George Grell is the lead developer there. Smoke, dust, and aerosol schemes, HER smoke, RAP smoke, WRF chem, a lot of that development has taken place within our group as well. We're moving toward the NOAA MP land surface model for our future land surface modeling efforts, and then the community land models lake model component that Tanya Smirnova has worked on. So we've taken these physics, the versions that existed in the early spring for the RRFS model potential implementation, and worked to port those into MPAS. They exist now in our MPAS code base, which has been updated to the current version 8.2.2 as what we're calling the HER v5 suite. So we've defined that as a suite. Anyone who goes to our GitHub page can download that model and run it with our physics, should they be interested in doing so. I'll speak a little bit about workflow. Janet Derrico presented on this at the WRF MPAS users workshop earlier this summer. The details of the figure here are not particularly important, but starting here on the left, this text that is very fine in here is written in YAML, yet another markup language. And this is how we do our model configuration. Rokoto, a tool developed internally within NOAA to do our automation and workflow management. And then these feed into the unified workflow drivers that exist within the unified workflow tools. So this helps to streamline actually executing the model in real time as compared to what you might do with downloading the source code, compiling it, configuring it, running it by submitting it to a job scheduler, and then doing those tasks manually from there. So these drivers ultimately help prepare the run directories, define the resource requirements, run the model and all of the other components such as the tracker, the post-processors, and ultimately validate the configuration. So now to get into some of the results. I've used this emoji and color-coded chart here to depict our history of storm forecasts for the season. So sad faces mean we don't really have any forecasts for those. Big grinning faces with the green mean, yes, we have nearly complete forecasts throughout that storm's life cycle. Generally speaking, while we have a forecast for Beryl and a couple for Debbie, Francine, apart from the very beginning of its life cycle, through to Oscar, with a couple of exceptions, like Nadine was too weak for our model to track, and so we don't have forecasts there. Some of these here in the middle part of the season, such as Isaac, Leslie, were too far to the north or too far to the east in our domain, since it did not cover the full Atlantic basin for us to capture in their entirety. We have about 70 total forecast cycles over these cases. So I'll be presenting a lot of charts that look like this one over the course of this presentation. So taking a moment to kind of orient ourselves. For this one, this is track. So on the y-axis is the mean position error in nautical miles, getting away from SI units, as that is the typical unit that the National Hurricane Center uses for their verification activities. So this chart extends 0 to 500. Forecast hours on the x-axis, 12, 24, 36, 48, 72, 96, and 120, the common forecast hours that are evaluated by the Hurricane Center for forecast evaluation. Different colored bars represent different models or forecasts. The blue will always be the National Hurricane Center's official one, and that will always be the first one in these clusters of bars. Orange is our MPAS forecasts, will always be orange and will always be the second one. The next two will also always be the same. The green and the red are the two versions of NOAA's Operational Hurricane Analysis and Forecast System, or HAFS. And then for track here, this is NOAA's Operational Global Model, GFS version 16. That won't be in the intensity ones, and I'll get to that in a few moments here. But focusing on the orange bars at each of these forecast hours, through 72 hours, and even to some extent through 96 hours, our forecasts are quite competitive in this matched evaluation, where we're only considering forecasts from where all of the models had a forecast for that storm at each lead time. Our MPAS forecasts were quite competitive with the official forecasts as well as NOAA's operational modeling suite. Once we get to 96 and then especially 120 hours, performance becomes a little bit more degraded. These are primarily associated with storms in the far eastern portion of the North Atlantic Basin, Gordon in particular, but also Kirk and Leslie, which turned northward, recurved in the eastern to central North Atlantic Basin. And I'll go into a little bit of detail as to what's going on with some of those toward the end of my presentation. But by and large, comparing just these orange and the purple bars, 12, 24, 36, 48, 72 hours, our performance compared to the operational GFS, which we're using to initialize and provide boundary conditions for our forecasts, are very similar, which suggests that our downscaling, to some extent, of the GFS is working pretty well through at least 3 days' time here. I will note that that similarity through 72 hours is kind of masking some of the storm-to-storm variability, which will show up in some of the case studies later in the presentation. Breaking this down not just into the total track error, but in terms of a long track and a cross track. So a long track, differences in storm speed, a cross track, differences in storm direction. A long track errors in red and a cross track errors in blue, where positive values are too fast or toward the right of what was actually observed. The blue line here for a cross track is very close to zero, maybe a slight left of track bias at longer lead times. But our long track error starts near zero through about 2.5 days and then becomes increasingly slow biased with time. And again, that's largely driven by those storms out in the eastern and central North Atlantic Basin, for which we were too slow in turning them northward as compared to what actually took place. Now for intensity, similar orientation to the chart, except here we have mean absolute intensity error on the y-axis in knots, consistent with NHC practices, 0 to 50 knots here. The purple and now the addition of a sixth brown bar here, instead of the GFS, which is not at fine enough resolution to adequately be able to represent the intensity of a tropical cyclone, we now have the statistical dynamical models, decay ships, and the logistic growth equation model, or LGEM, that the Hurricane Center has used extensively for a number of years as part of their intensity forecast suite. But again, looking at the orange bars here, the first thing that stands out is that the orange bars stand above. And what we want is the orange bars to be lower. We want lower errors. They stand out in a bad way here at 12 and 24 hours. We don't have data assimilation in our system, so we're reliant on what the GFS at a 1/4 degree grid spacing provides us. And when you have a storm like Hurricane Milton in the Gulf, that was one of the most intense storms on record in the entire Atlantic Basin, very small and compact, GFS is like Category 1 hurricane, right? No. So at the very short lead times, our forecasts for those high-end storms really struggled, and I'll be able to show examples of that in a few moments. Yet, despite that, by the time we get to 36 and 48 hours through at least 3 days, our forecasts are quite competitive with the official as well as NOAA's operational hurricane model systems. Despite no data assimilation, despite no ocean coupling, our physics rapidly implemented into MPAS, no tuning taking place. We believe this is a pretty good result, all things considered. even out to 96 and 120 hours. Though the hurricane models half A and half B had really good seasons for these storms, we were still very close to the National Hurricane Center's official forecasts. Errors were somewhat larger. Again, those storms in the eastern and central North Atlantic, Gordon in particular, being challenging. We can also look at the biases as opposed to just the total errors. Red is the mean sea level pressure bias. Positive values are too weak. Blue is the 10-meter wind speed bias. Positive values are too intense. Generally, we'd expect these to have opposite sense to each other. So here we can see the problem at initialization. Our storms are too weak, on average 10 knots and about 5 hectopascals, largely driven by those very intense storms comprising about a tenth to a seventh or so of our case data set. And then through 84 hours, we're slightly weak biased. Several hectopascals too weak, several knots too weak. But then that flips at those later lead times with fewer cases. Gordon in particular, our forecasts were way too intense as compared to what actually happened, a weak storm that ultimately dissipated in the central Atlantic. So I want to go for the last half of the presentation to talk about some case studies. Two of our most notable storms of the season, Milton, one of the most intense storms on record in the Gulf of Mexico. We'll talk a little bit about our track and intensity forecasts for Milton, which, spoiler, yay, we were very, very happy with these. Simulated eye-wall replacement cycle, we were also able to see in multiple different forecast cycles this MPAS being able to resolve the internal dynamics to produce forecasts of explicit eye-wall replacements that were very similar to what occurred in reality. Hurricane Helene, of course, the catastrophic flooding in the southern Appalachians. We'll take a look at some of the precipitation forecasts associated with that. And then Gordon, I've alluded to several times here. Spoiler, take a look at some of what's going on with the track and intensity forecasts from our modeling system there. So starting with Hurricane Milton, a spaghetti chart of track forecasts. So on the upper right here are the different forecast cycles, day followed by hour of initialization. Lighter colors are the earlier forecasts, darker colors are the later forecasts. The solid black line in this chart is the observed track of Milton from its origination here in the western Bay of Campeche through to the northern tip of the Yucatan and across Florida to the north of the Bahamas. We have black text in small print along each of these tracks denoting 12-hour forecast points. So the thing to pick out, apart from this first track here of Milton being too far to the north in the central Gulf of Mexico, there's very tight clustering of the forecast tracks along the actually observed track through to landfall south of Tampa Bay in the Florida Peninsula. The black text, each of our forecast cycles is 12 hours off. So if you have successive forecast cycles where those 12-hour labels are nearly on top of each other, that indicates good consistency from one cycle to the next in terms of where MPAS was predicting Milton to be. And there's a lot of clustering of those black labels along the track. So very tightly packed, close to the observed track, very consistent forecasts up until landfall after that first model cycle. And so perhaps unsurprisingly, looking at our track forecast verification, our orange bar here, 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 and here, our forecasts were very, very good. And in fact, better than the National Hurricane Center's official forecasts at most lead times, better than the rest of NOAA's operational modeling suite at most lead times for MPAS. And we found that to actually be true for most of the Gulf of Mexico storms, Francine, Helene, and Milton this year. Work is underway to figure out maybe just why that might be the case. If we're drawing a lot of value from the GFS lateral boundary conditions on the western edge of the domain, that might have been particularly good, yet we're still improving quite a bit on the GFS, comparing the orange and the purple bars at the later lead times in particular, improving by 50 or more nautical miles at most of those lead times. So it's not going to just be that, small sample sizes notwithstanding. Intensity, there's some things to like and some things to be like, well, okay, maybe we can do better on this in the future. So here the dashed black line is the observed intensity trace from the National Hurricane Center's preliminary best track for Milton, showing its peak at about 150 knots here in early October. Dip here associated with an eye wall replacement cycle, re-intensification, and then some fluctuations with continued eye wall replacement, and then intrusion of mid-latitude dry air and vertical wind shear near landfall. Our initial forecasts here that start close to the observed intensity, the GFS was able to resolve that well in the initial conditions, show these intensity traces pointed straight up. The rate of intensification was very similar to what was actually observed with Milton, which was on the far upper bound of what is present in the Atlantic historical record. Not able to quite capture the peak, most of these forecasts leveled off at category 4 intensity between about 115 and 135 knots for their peak intensity. But the rate of intensification was very similar up until that maximum intensity point as compared to what was observed. But then we get to some of the later forecasts. Milton has undergone rapid intensification and is very intense. The GFS initial conditions are not able to represent that well. So our forecasts, these dots here that I'm tracing along with my laser pointer, are the beginning intensities, significantly weak biased by as much as 80 to 90 knots at those initializations. So the model tries to play catch up in the first 12 to 24 hours. It recognizes, given the environment and the storm structure that's there, that it should be more intense than it actually is. So it spins up the intensity toward category 3-4 range, but it's not able to ever quite catch up to what was observed. We do see some fluctuations in these different forecasts here near peak intensity, and these are associated with simulated eye wall replacement cycles in the model forecasts, and I'll show an example of that in a few moments. Then the better constrained physical problem of decay near landfall was reasonably well predicted, the rate of decay as well as the magnitude of decay from where the model thought that it was at that time through to ultimately Milton's dissipation was reasonably well predicted. So looking at the overall forecast verification statistics, yeah, this orange bar stands above, like I, with my height, tend to stand way out, not in a good way in this case for the MPAS forecasts. Nearly 30 knots average intensity error over 10 forecasts at 12 hours. But by 24, it's coming in range of the dynamical statistical models, decay ships and LGEM. And then by 36 hours, it's the second best performer, only beaten by one of the two operational hurricane models from NOAA. And it remains competitive through to most of the later lead times. So despite that lack of data assimilation in our forecasts, the model is able to spin up to something reasonably, at least in the context of the official forecast and the operational hurricane models, reasonably close to what was actually seen with Milton. So looking a little bit more at Milton's structure as it was simulated within the model, here is a depiction from NOAA's Hurricane Research Division from reconnaissance aircraft, flight between the 8th of October 2141 UTC to the 9th of October 0046 UTC. It's about a 3-hour period with multiple passes. You can see these thin black lines here depicting the aircraft transects. This is reflectivity at 2 kilometers as well as the 2 kilometer above ground level wind here at left. And then here at right is the 2 kilometer above ground level wind speed, which is shaded. And then the thin streamlines are 2 and 5 kilometer winds as assessed by the reconnaissance aircraft. So here we have a very small diameter inner eye here, very fine, 5 to 10 nautical miles in diameter. And then this nascent larger outer eye wall here of about 50 nautical miles diameter, give or take. With a very compact wind field, the purples here are 64 knots and greater, so hurricane force, confined to within about 50 kilometers north, south, east, and west of the center at this time. A corresponding MPAS forecast, initialized 2 days prior to this time, shows a primary eye wall that's not as small as what was observed. The model is not able to, with its effective resolution in the ballpark of 15 to 20 kilometers, not quite able to depict that small 5 nautical mile diameter eye, but it does depict this inner smaller eye and then this rain band congealing into a nascent secondary outer eye wall with larger radius, as well as this expansive outer rain band to the north and west that you see hints at from the flight legs from northwest to southeast and west to east here as well, with a similarly compact 34-knot wind field around the center of the storm. If we go forward just about 12 hours, October 9th, 9:21 to 13:28 UTC, back to the data, there's a very small remnant inner eye, but at this point, the inner eye has just about completed dissipation, taken over by this larger outer eye wall of about 50 nautical miles in diameter. The 64-knot, the hurricane wind field, has become larger, especially to the east, and it's become more asymmetric toward the south and toward the east as the storm begins to experience the negative effects of an upstream trough and vertical wind shear to its west. And in our model, by this time, here looking at 12 UTC, so a 60-hour forecast, we see this remnant inner eye wall here as well, and this primary much larger outer eye wall has become dominant, and over the course of the next 6 hours, that inner eye wall completely goes away. This 64-knot wind field has increased in size. I'll go back to this image and this image. These cover the same horizontal extent, although it's not yet become more asymmetric. So we were encouraged to see our real-time forecast being able to explicitly depict in multiple model cycles, of which I've just shown one, this outcome of internal storm dynamics with the eye wall replacement cycle, both that it captured it at all, but also that it captured it reasonably close to the timing of what was observed to 2 to 2.5 days lead time. So I'll shift gears here to Helene. This is an overview from our MPAS forecast, this being the 25th of September 0 UTC forecast cycle. Those initialized from the 24th through the 26th, they're all pretty similar, so I've chosen this one as a representative example of about 6 different forecast cycles. Depicted here is composite reflectivity and color shading here at right, and then the 10-meter wind field with the barbs per the standard convention. Just to lay the land here. Helene intensifies as it moves through the eastern Gulf, makes landfall to the southeast of Tallahassee, Florida, in the Florida Big Bend region, and then moves north-northeastward and then ultimately north and northwestward into the southern Appalachians, producing copious catastrophic amounts of rainfall and flooding into the southern Appalachians. Overall, our track forecasts were very good for Helene as well. I'm not going to go into the specific statistics of that, but instead focus a little bit more on the precipitation. So this is a sequence of 24-hour estimated and forecast precipitation, observations from the multi-radar and multi-sensor system here at left, our MPAS forecasts here in the center, and then MPAS minus MRMS here at right. So green on the rightmost panel depicts MPAS predicting too much rainfall over that 24-hour interval, brown too little rainfall. And the color tables range from 1/100th of an inch to 25 inches for the left 2 panels, and minus 12 to plus 12 inches for the right 2 panels. Relatively large color ranges given the amount of rainfall that fell. Broadly speaking, there's a fair bit of agreement. But when you get into the details, especially highlighted by the difference chart here at right, there are some noteworthy differences that emerge. In particular, we have too much rainfall along the coast. The warm, moist inflow on the east side of Helene ascended over a pre-existing stationary front across the southeast United States. And so we perhaps have too efficient of rain microphysics taking place with that area of rainfall, producing consistently too much coastal rainfall on the order of even 10 inches too much over these 24-hour periods. Up here into the Carolinas, generally slightly underdone. Even in the mountains, the forecasts were for quite a bit of rainfall, 15 to 20 inches, a little bit under what was actually observed as estimated through MRMS. But these convective rain bands, these outer rain bands, were insufficiently convective in our MPAS forecasts. This area in our forecast was dominated by a broad expanse of stratiform precipitation. The reality was associated with that broad stratiform precipitation with elevated convection aligned on north-south corridors that produced locally heavier rainfall in western and central South Carolina into central North Carolina here. So more work is necessary for us to dig into our microphysics in particular to be able to better understand not just the what, but more of the why. And then finally going on to Tropical Storm Gordon. This one, again, the black line is the official NHC track. NHC ceased tracking it operationally around here, about 20 degrees north, 50 degrees west. The remainder of this track is tracking it as a remnant disturbance or a remnant low. We have our forecasts, again, the light blues to the dark purples representing different forecast cycles over about a 5-day period here. Noting that our earlier forecasts, several of these kept Gordon tracking more toward the west, and then ultimately those that did turn it more toward the north were biased to the west. This being about 1 to 2 degrees longitude, so roughly 150 or so kilometers too far to the west at some of these later points along the track for Gordon. I'll note that the Hurricane Center's standard practice is that if the storm is no longer classified, those forecasts generally no longer enter into the forecast verification, which can unfairly help a model if the model's saying 80 knot category 1, category 2 hurricane, and it's actually dissipated. Well, that typically doesn't enter into the official statistics, the official verification. Since there was actually a track and intensity here, we feel that it's a more fair comparison, especially since our interest is in making the model the best that it can be, to see, all right, if it's forecasting this storm to be coherent and much more intense than in reality, what does that actually look like? And so that shows up really well here for the intensity forecasts. The dashed black line, again, is the observed intensity. And I put this vertical black line here to denote when the Hurricane Center terminated forecasts for Gordon on September 17th at 12 UTC. They continued to track its intensity and location as a disturbance for 3 days thereafter, but it did not actually exist as a tropical cyclone. And conveniently, or not conveniently, our model thought not only is it actually a tropical cyclone, but it's an intensifying tropical cyclone, with several forecasts depicting it reaching category 1 hurricane intensity during a period where it was a non-closed area of low pressure with 25 to 30 knot maximum sustained winds. So while the earlier forecasts, intensity-wise, keeping it relatively weak, were pretty good, those longer range times later on in Gordon's life cycle were not so good. So what could be going on here? So this analysis here is looking at a representative forecast cycle, this being 14th of September at 12 UTC, so sort of earlier in Gordon's life, valid at 19 September 12 UTC. So this is a 5-day forecast from our model. I'm taking the MPAS forecast and subtracting out the corresponding GFS analysis as a proxy for observations or for truth, looking at the 850 to 300 hectopascal wind difference as a proxy for the steering flow for the cyclone. So looking at differences in how the steering large-scale environment for Gordon is represented in our model versus in the proxy for reality from the GFS analysis. And we also do that in the black and red contours for the 500 hectopascal height, where the MPAS forecast is in solid black and the GFS analysis is in the solid red. Anticyclonically turning winds indicate where the model has 2 anticyclonic of steering flow. Cyclonically turning winds are where the model has 2 cyclonic of steering flow. And we have Gordon here with cyclonically rotating wind barbs. Gordon was far stronger in the MPAS forecast than in the corresponding GFS analyses. And it's paired with this anomalously strong anticyclonic steering flow to the northeast and a displacement of an upper level low further to the west, to the north of Puerto Rico, northeast of Hispaniola, well to the west of where Gordon was. So we hypothesized that this anomalously favorable environment with anomalous subtropical ridging here in the eastern and central North Atlantic is responsible both for Gordon being in a more favorable environment to maintain and then ultimately increase its intensity, but also helping to steer it further to the west initially, and then some of the later forecasts have this displaced a little bit further to the east. One of our developers, Joe Olson, has told me that we've seen this type of structure in our FV3-based forecasts for earlier hurricane seasons. Too much anticyclonic flow in the central and eastern subtropical Atlantic. So whether that's an issue with our physics, potentially with our representation of shallow cumulus, given that it seems to be consistent across modeling systems, dynamical cores, it's something that we plan to investigate further as we go forward. So to wrap up, with an eye toward the future, overall we were pretty pleased with how MPAS performed in real time with our physics, without data assimilation, without ocean coupling, for track and intensity forecasts for this highly impactful Atlantic hurricane season. We're looking to continue to develop our physics, but also our data assimilation through JEDI and our workflow capacities for MPAS, with eyes toward initiating real-time global MPAS forecasts, probably between 12 and 15 kilometer grid spacing, sometime in the first part of 2025, and then ultimately the second iteration of the rapid refresh forecast system over North America at high resolution, targeted for 2028. As I noted, our team working on data assimilation is just about at the point of being able to test in real time JEDI coupled to MPAS with our other existing data assimilation workflows. And so we expect our real-time forecasts to begin utilizing cycled data assimilation early in 2025, which will really help us better assess biases within our model physics. Rather than utilizing an external product that's cycled differently from our physics, we'll be able to continuously cycle with our physics, so those biases will hopefully be able to emerge a little bit more clearly than they do in these cold-started hurricane forecasts, as well as our CONUS forecasts. They'll also provide for better spun-up model initial conditions. GFS doesn't have any of the microphysical fields in it. We'll be able to cycle our microphysical fields to be able to have a better resolved storm structure at the initial time, both precipitation-wise and consistent with our horizontal grid spacing. Preliminary scoping of the work that's needed to bring the MPAS dynamical core into the Unified Forecast System, or UFS, has begun, though the work itself is not yet funded. NOAA has just released an internal Joint Technology Transfer Initiative funding opportunity, of which one of the 9 funding opportunities is work to bring the MPAS dynamical core into the UFS. So there are groups at GSL, NSSL, and EMC, the Environmental Modeling Center in DC area, that are looking to put together a proposal to advance that work a little bit further along. And getting MPAS into the UFS will help us in particular with being able to couple to an ocean model. We don't have the capacity to couple MPAS standalone to an ocean model. We don't really have the capacity to learn another modeling system where that capacity already exists. So we're to some extent reliant on MPAS coming into UFS where we have an ocean model available to be able to do those coupled ocean atmosphere forecasts. And then specific to hurricane applications, I've shown a lot of what here and not a lot of why. We're just beginning the search as to why. Developing hypotheses based off of what we're seeing to then inform how we dig into the model data to better assess what's going on, to hopefully be able to help improve our physics parameterizations, which have generally not seen a lot of testing for tropical cyclone applications, at least not within our lab. And for next year, we'll participate in the 2025 Hurricane Forecast Improvement Project. We're looking at possibly both a larger regional domain to be able to capture more of the Atlantic Basin, but also more of the features steering storms within the Atlantic Basin. So something entirely North America toward 0 degrees east, as well as a global domain, coarser global, refined to finer scale over the North Atlantic Basin as part of our larger global grand challenge. So with that, thank you for your time and for your attention. I'm happy to take any questions that you all may have.
Thank you very much, Clark. Very exciting to see these initial results, and it seems like it'll be really promising as we update the assimilation warm starts. So we'll take questions from the room and on Slido, one of each. Our first question here.
Clark, one of the real interesting aspects of Milton was the outbreak of tornado supercells in southeast Florida. Have you had a chance to see how MPAS represented that?
We haven't as of yet, but that's a good thing for us to look into. And I think you stole Dan's question over here once again. So, but no, thanks for bringing that up. We do have the output to be able to do that type of diagnostic. We just haven't focused on that as of
Yeah,
yet.
because that was a really unique event, as well as, the other aspects of Milton.
Indeed.
All right, we'll take a question online. We have a question. Did we have any comparison against HWRF?
So though there are HWRF data in the forecast cycle or in the forecast fields, we did not do an HWRF comparison since my knowledge is HWRF development is frozen. Everything is with halves A and halves B. And so we didn't feel that it would be the most appropriate comparison of our forecasts against what NOAA is actually producing for hurricane applications at this point.
Hi, Clark.
Hi, George.
Good to see you.
Likewise.
I have two somewhat related questions about moving fine meshes. As you know, the HAFS and HWRF has moving fine mesh. I was wondering, do you have any intuition or initial thoughts on whether these results are more related to the moving fine mesh that HAFS has, or just the fact you have higher resolution everywhere, which may be a benefit? And then how crucial is that for your research group to have a moving fine mesh capability?
Yeah, so the first one, I should reach out to Gus Alaka and his group at HRD to see if they have tracker data for the basin scale halves, halves M, to be able to assess some of what you're saying for the first question, although I think they do have the moving nests inside of there as well. So it's not a clean comparison even there, but I think it'll be a little bit better than the individual storm halves A and halves B. Movable finer refinement meshes for us at GSL are not crucial. I think we're content with just putting higher resolution over a larger area, such as the entire North Atlantic Basin. But since we're not looking to make an operational hurricane model, we can kind of get away with that. A group like AOML, HRD, might say something very differently. I know that they've been very concerned about computational requirements, naturally because they have to be. So for us, not so crucial. If it means that we go to 2 kilometers and it's over the entire basin, well, more impetus for NOAA to add more supercomputing resources for our development purposes. But for HRD, I think it'd be a very different story.
Okay, we have a question online from Jonathan Vi. How did MPAS do in representing the extratropical transition of Milton near and after landfall? And have you evaluated the footprint of winds over land for this event, rainfall over the Tampa area?
Yeah, it's a great question, Jonathan. In terms of the extratropical transition and overall decay of the storm near and after landfall, it did fairly well. It showed rapid decay of the storm and rapid asymmetric structural development, although we haven't looked at that quite as closely as some of the other fields as of yet. Footprint of winds over land and rainfall, we haven't looked as extensively at that quite yet either. So more focused on larger scale and then what we saw at peak intensity over the ocean with Milton to this point. But we'll dig into those aspects a little bit more as we get into the off season as well.
So this is betraying my ignorance because I haven't been keeping up as much with MPAS lately. So this regional mesh, is that still embedded in a larger global mesh, or do you actually have it have boundary conditions from like the GFS or something? How does that work?
Yeah, so this regional has boundary conditions provided by the GFS. It's a cutout, I believe, of the global 3 kilometer mesh.
Great talk, Clark. James Pinto on RAL. Question about initiation of the cyclones. Have you looked at that at all in terms of if it has a tendency to false alarm with initiations, or is it able to capture the initiation of the systems? Or are you just relying on GFS to provide the information of where the storms are?
Yeah, so the forecasts themselves were reliant on GFS to provide initial conditions, but of course thereafter it can evolve freely, somewhat freely from that. We haven't seen any indication that it's generating too much false alarm in terms of cyclones that didn't actually exist. but part of that's probably also the limited extent of our domain and the fact that we generally have forecasts from mid-September through the end of October. There's usually something or multiple somethings in the Atlantic Basin throughout that time period. Our deepest analysis has been on the so-called invest areas that the Hurricane Center is tracking but aren't yet tropical cyclones, and some of which don't become tropical cyclones. Generally speaking, our forecasts correctly predicted when they would and would not become tropical cyclones for those weaker disturbances.
Just a quick follow-up, it just reminded me that there was that one false alarm that a lot of the models had later in November that was predicted to go across Florida as a sort of a longer range system. That might be interesting to see.
Yeah, that one, even though the HFIP reservations on NOAA supercomputers extended to, I think, cover that, we did not actually have our forecast system running. We were trying to do some retrospective runs to backfill for Francine and Debbie at that time. But it would be interesting to look at in hindcast mode.
Okay, it's good to see a lot of good questions online as well. We have one, do you think MPAS data assimilation would have improved the accumulated precip errors in the Helene case?
Yeah, it's a good question. I don't know that I have a really good answer for that. So we certainly are having to spin up the microphysical fields on our own over the course of the 1 to 5 days leading up to Helene's landfall. Whether constraining those better initially would have changed the outcome, I really can't say at this point. I think we'd have to run experiments with our cycled DA system to do that. And I'm not sure we'll have the capacity to do that in hindcast mode.
All right, we got a couple more questions.
Hi, Claire. Great talk. I have two questions. So one is, have you constructed any like early models? Because for Milton, you have those probably high errors. So maybe a early model, according to NHCP may help. And also, have you compared MPAS forecast when the storm is weak and compared to when the storm is a stronger one? Do you still see the initial high intensity errors?
Right. For the first part, no, we haven't done that at this point. For the second part, generally speaking, when the storms were weak at initialization, the intensity forecasts, at least through 2 to 3 days, were pretty good. For the stronger storms, they were clearly pretty bad because we weren't able to resolve that initial intensity, but we haven't done a formal separation. I think part of that is with our small sample size. 70 forecast cycles in total. I think those that are at category 2 and above intensity is probably more like 15 or so. So I think something like the Milton case study, and we see it for Helene and Francine to lesser extent as well. I think that's what we would see from that type of analysis.
Hi. First of all, it's great to know at least somebody in Boulder is doing real-time hurricane forecasts.
Yes.
We've been doing, well, we did that a while back, but then stopped doing it, so that's great. Now my question is, in the beginning you alluded to the issues the FE3 has with representing convection. Now the HAFS models are based on the FE3. Do you think this issue is not as detrimental when it comes to hurricanes, or have you compared structures, let's say reflectivity, HAFS versus MPAS, even if the grid spacing isn't exactly the same? Is there some way to assess whether MPAS is more accurate in representing convective structures of the TCs?
Yeah, we definitely could do that, but we haven't done that as of yet. We've asked ourselves those questions as well of, if FE3 is so ill-suited for deep moist convection over CONUS, shouldn't we also see some of those issues potentially with hurricanes at 1 to 3 kilometer grid spacing? I think to some extent the environments are a bit different. The interior of a hurricane is not nearly as unstable as what you'd see over CONUS in May, for instance. So the updraft magnitudes might not be quite as intense. And I think the organization on the storm scale, the really meso to synoptic scale as compared to more of the meso down to micro scales with the CONUS convection, probably helps FE3 a little bit there as well. But I have seen, at least for coarser hurricane-related applications, there are issues with FE3 convective structures in those cases. Now, whether that's convection parameterization, the FE3 dicore itself, or some combination thereof, the authors weren't able to say. But I would suspect that there are probably some issues there that are being masked by the synoptic larger scale control and the tuning, extensive tuning that they've done for HAFS A and HAFS B. But we haven't gotten into details for that type of investigation. And as you might expect, it's a little bit of a thorny political subject as well. We're not the hurricane research division, yet we're doing real-time hurricane forecasts. NOAA's invested tens of millions of dollars into HAFS. It's going to be interesting when we do start to get into those diagnostics, just what ultimately emerges.
Thank you.
Thanks, Val.
Well, let's wrap it up here. Before we thank our speaker, I just want to mention, feel free to stop by to chat. And please, on your way out, take some homemade cookies so I don't have to take them all home. And let's thank our speaker again.
Yeah, thanks everyone. I have about 30 minutes that I can stick around, so look forward to hopefully chatting with some of you here.